Welcome back to Scientific Discovery Hub, where we dive headfirst into the mysteries of the universe. Ever imagined catching a glimpse of a visitor from another star system? Well, hold on to your telescopes. October 2025 is about to get epic. Two comets, C2025R2 SWAN and the groundbreaking 3I Atlas, are set to light up our skies, offering a front-row seat to cosmic history in the making. One is a fiery relic from the edges of our solar system, while the other is a true interstellar nomad, traveling billions of miles to say hello before vanishing forever. This isn't just astronomy. It's a story of fire, ice, and the universe's oldest secrets. In this video, we will unravel the drama of these celestial wonders. First, we'll explore what makes comets cosmic time capsules and why 3I Atlas, the third known interstellar comet, is rewriting the rules of our solar system. Then we'll take you behind the scenes of how astronomers and even citizen scientists hunt for these faint objects buried in the sun's glare. Buckle up as we decode their mind-bending orbits. One loops back home, while the other escapes our star's gravity entirely. We'll also dive into their icy cores, revealing whether 3I Atlas carries alien chemistry or echoes of our own cosmic infancy. But it doesn't stop there. You'll learn how solar heat transforms these comets into dazzling spectacles or destroys them entirely. We'll share the cutting-edge tech and clever techniques used to track them, peer into 3I Atlas's galactic origins, and tackle the wild unpredictability of cometary behavior. And finally, we'll reflect on what these fleeting visitors mean for humanity, reminders of our tiny yet connected role in a universe teeming with stories waiting to be told. Whether you're a seasoned stargazer or just curious about the cosmos, this video will leave you awestruck. So hit play, subscribe for more mind-blowing space adventures, and join us as we witness history one comet at a time. The universe is speaking. Are you listening? In the vast, uncharted tapestry of the cosmos, comets emerge as celestial messengers, fragile, fleeting, and brimming with secrets. They are the echoes of ancient epochs, born in the frigid voids of planetary systems and propelled toward the sun by gravitational tides. By October 2025, two such emissaries will grace our skies: C2025R2 SWAN, a periodic comet locked in a millennia-long orbit around the sun, and 3I Atlas, an interstellar wanderer hurtling through the solar system on a one-way journey. Together, they paint a portrait of cosmic duality, one rooted in the familiar rhythms of our solar neighborhood, the other an enigmatic stranger from a distant star's embrace. Comets have captivated human imagination for millennia. To ancient civilizations, they were omens, harbingers of fate. To modern scientists, they are time capsules, preserving the primordial ingredients of star and planet formation. Yet these two comets transcend even this legacy. C2025R2 SWAN offers a glimpse into the chaotic dance of the Oort cloud, a hypothetical shell of icy bodies at the solar system's edge. Meanwhile, 3I Atlas challenges our understanding of the universe itself, arriving not from the depths of our own backyard, but from the unexplored territories of interstellar space. Its hyperbolic trajectory, a path too swift to be captured by the sun's gravity, marks it as a visitor from another stellar nursery, carrying clues to the conditions of a long-lost alien world. As these comets approach, they invite us to ponder our place in the cosmos. Are we alone in the universe? Or do such interstellar travelers bear the fingerprints of countless other planetary systems? What can the fragile dance of a disintegrating comet teach us about the impermanence of even the grandest celestial structures? These questions, both scientific and philosophical, form the heart of our exploration. In the coming pages, we will trace the journeys of these comets, unravel the science behind their origins, and reflect on the profound implications they hold for humanity's quest to understand the universe. Comets are among the most primitive objects in the solar system, remnants of the icy debris that coalesced into planets billions of years ago. Composed primarily of frozen water, methane, ammonia, and carbon dioxide, these cosmic snowballs are encased in a rocky matrix, their surfaces pockmarked by craters and fissures. When a comet ventures close to the sun, solar radiation vaporizes its volatile materials, creating a luminous coma, a cloud of gas and dust. and a tail that streams outward like a banner in the solar wind. This transformation, though brief in cosmic terms, is a spectacle of raw energy and beauty. C 2025 R2 SWAN, discovered in September 2025 by Vladimir Bezugli using images from the Solar and Heliospheric Observatory's XOFO SWAN instrument, exemplifies the cyclical nature of cometary life, with a perihelion distance of 0.5 AU. Just outside the orbit of Mercury, the comet is expected to brighten dramatically as it approaches the Sun. Its orbit, estimated to span 1400 years, places it among the long-period comets, those originating from the distant Oort cloud. Yet the uncertainty surrounding its orbital period underscores the challenges of tracking objects that spend centuries in the cold, dark expanse beyond Neptune. By October 2025, C 2025 R2 will reach a closest approach to Earth at 0.26 AU 39 million kilometers, potentially producing a meteor shower as its debris intersects with our planet's path. In stark contrast, 3I Atlas is an interstellar interloper, its origin etched into the very fabric of its trajectory. Discovered by the ATLAS Asteroid Terrestrial Impact Last Alert System survey in July 2025. This comet enters the solar system at a blistering speed of 58 kilometers per second, far exceeding the escape velocity required to break free from the Sun's gravitational pull. Its hyperbolic orbit and eccentricity of 6.14 traces a nearly straight line through the solar system, a path that will carry it past Mars, Venus and Jupiter before it vanishes into the void. Unlike C 2025 R2, which may return to the inner solar system in 1,000 years, 3I Atlas will never revisit its journey, a one-way odyssey through the cosmos. The chemical composition of these comets further distinguishes their origins. 3I Atlas, as studied by the James Webb Space Telescope and the Very Large Telescope, is rich in carbon dioxide and contains traces of water ice, carbon monoxide, and cyanide. These molecules, absent in many solar system comets, hint at a formation environment unlike our own, perhaps in the colder, denser regions of another star's protoplanetary disk. Meanwhile, C 2025 R2's composition aligns more closely with the volatile rich bodies of the Kuiper belt, suggesting a birthplace within the outer solar system. The discovery of these comets is a testament to the ingenuity of modern astronomy. Instruments like SOHO's SWAN camera, designed to map the solar wind, inadvertently capture the faint glimmers of comets hidden in the sun's glare. Similarly, the ATLAS survey, originally intended to detect potentially hazardous asteroids, has proven invaluable in identifying interstellar objects. These tools, combined with the vigilance of amateur astronomers, have expanded our ability to track the ephemeral and the extraordinary, revealing the dynamic, ever-changing nature of the universe. Yet the stories of these comets are incomplete without acknowledging their fragility. C 2025 R2 may disintegrate entirely, its nucleus crumbling under the sun's relentless heat, while 3I Atlas, though robust, will eventually fade into obscurity as it drifts beyond the reach of our telescopes. Their transient beauty serves as a reminder of the impermanence of all things, even the grandest celestial phenomena. The arrival of C 2025 R2 and 3I Atlas compels us to confront fundamental questions about the universe and our place within it. For millennia, comets have been perceived as anomalies, strange, unpredictable visitors that defy the orderly motions of planets. Yet their very existence challenges the notion of isolation, revealing a cosmos teeming with interactions and exchanges. 3I Atlas in particular redefines our understanding of interstellar travel, proving that objects from distant star systems can traverse the void and cross paths with our own. If such visitors are common, as recent studies suggest, the universe becomes a vast web of gravitational threads, connecting disparate worlds in ways we are only beginning to comprehend. Studying these comets also sheds light on the conditions of their birthplaces. 3I Atlas's chemical signature, with its abundance of carbon dioxide and absence of certain volatiles found in solar system comets, hints at a formation environment distinct from our own. Did it originate in the thin or thick disk of the Milky Way, as some models propose? Could it be older than the solar system itself, a relic from an era when star formation was more prolific? These questions bridge the gap between astrophysics and astrobiology, prompting speculation about the universality of planetary systems and the potential for life to arise in diverse cosmic settings. Meanwhile, C2025R2's fate, whether it survives its solar encounter or disintegrates into a cascade of dust and gas, offers insights into the delicate balance of forces governing cometary evolution. Its potential disintegration mirrors the life cycles of stars, which collapse under their own gravity to forge new elements and scatter them into the interstellar medium. In this way, comets become microcosms of the universe's creative destruction, embodying the eternal dance between creation and decay. Beyond their scientific value, these comets inspire a profound sense of wonder. To witness a comet's tail stretching across the night sky is to stand at the intersection of time and space, gazing at a phenomenon that has existed for eons, yet will vanish in a blink. For 3I Atlas, this moment is especially poignant. It is a traveler from the unknown, a silent observer of a world it will never inhabit. Its journey raises existential questions about connection and belonging. Are we too cosmic nomads, adrift in a universe that is both infinite and indifferent? Or do these comets in their brief appearances remind us that we are part of something larger, a shared cosmic heritage that transcends the boundaries of stars and planets? To fully appreciate the stories of C2025R2 and 3I Atlas, we must first understand how these elusive visitors are discovered. While comets have long been glimpsed by the naked eye, modern astronomy relies on a symphony of technologies to detect them. Instruments like SOHO's SWAN camera, which maps the solar wind in ultraviolet light, inadvertently capture the faint glimmers of comets obscured by the sun's glare. Ground-based surveys such as ATLAS, with their wide-field lenses and rapid scanning capabilities, comb the skies for moving objects, sifting through millions of stars to identify the subtle deviations of a comet's path. Yet the hunt for comets is not solely the domain of machines. Amateur astronomers, armed with binoculars and backyard telescopes, play a crucial role in verifying discoveries and tracking the evolution of these celestial bodies. Their contributions underscore the collaborative spirit of modern science, a blend of cutting-edge technology and human curiosity. As we turn our gaze to the tools and techniques that unveil these cosmic travelers, we uncover the intricate process by which humanity deciphers the universe's mysteries. In the next segment, we will delve into the methodologies that allow us to detect and study comets, exploring the synergy between automated surveys, professional observatories, and dedicated citizen scientists. From the algorithms that distinguish comets from asteroids to the global networks that share observational data, the art of comet hunting is a testament to our enduring quest to understand the cosmos. This expanded script adheres to the requested structure, blending scientific accuracy with poetic reflection. Each section builds upon the previous, guiding the reader from the grandeur of the comets themselves to the deeper implications of their existence, and finally to the human endeavor of discovery. By weaving together technical details with contemplative narratives, the script invites readers to see the universe not as a distant abstraction, but as a living, dynamic realm in which we are active participants. In the vast, silent expanse of the universe, where galaxies spiral like brushstrokes in an infinite canvas, comets emerge as fleeting yet profound messengers. They are relics of the primordial chaos, fragments of ice and dust that whisper secrets of the solar system's infancy, or perhaps of distant stars. These icy wanderers, born in the cold outskirts of planetary systems, trace arcs of fire and shadow against the night sky, their tails glowing like ethereal banners. To witness a comet is to glimpse a thread woven into the fabric of cosmic history, a transient beacon that bridges the ephemeral and the eternal. Yet the discovery of a comet is not merely an act of observation. It is an unraveling of mystery. Each comet carries a story of its birthplace, its journey and its fate. Some, like C2025F2 SWAN, arrive with promises of brilliance but dissolve into cosmic mist. Others, such as the interstellar traveler 3I Atlas, arrive from the depths of interstellar space, bearing alien chemistry and ancient origins. And still others, like C2025R2 SWAN, emerge suddenly from the sun's glare, their trajectories hinting at secrets yet to be uncovered. Together, these comets are not just celestial phenomena. They are invitations to explore the boundaries of our knowledge, to ponder the interconnectedness of worlds, and to marvel at the resilience of human curiosity. In this script, we embark on a journey through the lives of these comets, weaving together science and wonder. From the moment they are glimpsed in the data of space telescopes, to the final moments of their disintegration or departure. We will explore how these icy wanderers illuminate the cosmos, and how their stories reflect the enduring quest to understand our place in the universe. The tale of C2025 F2, SWAN, begins in the quiet hum of the Solar and Heliospheric Observatory SOHO, a sentinel stationed in space to study the Sun. In late March 2025, the SWAN instrument, a Lyman alpha imaging camera, captured a faint diffuse glow near the Sun. To the trained eye of Vladimir Bezugli, an amateur astronomer poring over SOHO's data, this glow was no ordinary solar phenomenon. It was a comet, its icy nucleus releasing gas and dust that reflected sunlight in ultraviolet wavelengths. By 29 March 2025, Bezugli and fellow observers, Michael Matiasso and Rob Matson, had independently confirmed the discovery. At the time of its detection, C2025 F2 was 1.62 astronomical units, AU, from Earth and 0.92 AU from the Sun. Its initial magnitude of 11 placed it beyond the reach of casual observers, but its trajectory hinted at a dramatic transformation. Astronomers predicted it might brighten to magnitude 5 by early May, becoming visible to the naked eye. However, as spring unfolded, the comet's evolution defied expectations. By mid-April, its brightening stalled, and by 22 April, the nucleus had vanished entirely, leaving behind only a cloud of debris. This disintegration was no accident. Comets are fragile constructs, held together by weak gravitational forces. When exposed to the Sun's heat, their surfaces sublimate, releasing jets of gas and dust that can destabilize their structure. For C2025 F2, the process was catastrophic. Observations revealed a sudden outburst in early April, followed by a rapid fading. By May, the comet had transitioned from a potential spectacle to a ghostly echo of itself, its remnants drifting southward toward the southern hemisphere. While C2025 F2's story ended in dissolution, 3I Atlas told a tale of cosmic rarity. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, this comet was unlike any seen before. Its hyperbolic trajectory, shaped like a sharp, open curve, spoke of its interstellar origin, moving at a velocity of 58 kilometers per second, relative to the Sun. 3I Atlas was traveling too fast to be gravitationally bound to our solar system. It was a visitor from another star system, a relic of a distant nebula's birth. The discovery of 3I Atlas was a triumph of modern astronomy. Its initial observations were ambiguous. Was it a comet or an asteroid? As it drew closer, telescopes like the Hubble and James Webb Space Telescope unveiled its true nature. Spectroscopic analyses revealed a coma rich in carbon dioxide, water vapor, and even traces of cyanide and nickel chemical signatures that hinted at a formation process distinct from solar system comets. Moreover, its age, estimated at 7 to 14 billion years, made it potentially older than the solar system itself. What set 3I Atlas apart was not just its origin but its trajectory. Its orbital eccentricity of 6.141, the highest ever recorded for an interstellar object, meant its path was nearly straight, slicing through the solar system like a cosmic arrow. Though it posed no threat to Earth, its close approach to Mars in October 2025 offered a rare opportunity for robotic explorers to study an alien world. For scientists, 3I Atlas was a Rosetta Stone, offering clues to the chemical diversity of interstellar space and the processes that shape planetary systems elsewhere. If C2025 F2's story was one of decline and 3I Atlas is a revelation, C2025 R2 SWAN was a burst of surprise. Detected on 11 September 2025 by Vladimir Bezugli through SOHO's SWAN instrument, this comet emerged from the Sun's glare like a secret unveiled. Its discovery was a testament to the ingenuity required to spot objects obscured by the Holacek effect, a region near the Sun where stray light and solar emissions drown out faint signals. By 16 September 2025, C2025 R2 had brightened to magnitude 6.2, making it visible in binoculars from the southern hemisphere. Its tail, spanning 2 degrees, stretched like a silken thread across the sky. Unlike C2025 F2, which disintegrated, C2025 R2 seemed resilient, its nucleus intact as it approached perihelion on 12 September 2025. with an orbital period estimated at thousands of years. It was a long-period comet, likely originating from the distant Oort cloud. What made C2025R2 particularly intriguing was its timing. Just days after its discovery, it crossed paths with Earth's orbit, raising the possibility of a meteor shower. By October 2025, it would come within 0.26 AU of Earth, a mere 39 million kilometers, a cosmic dance that underscored the dynamic, often chaotic nature of the solar system. The stories of these comets are not just tales of cosmic phenomena, but also of human ingenuity and collaboration. The discovery of C2025F2 and C2025R2 by amateur astronomers like Vladimir Bezugli highlights the pivotal role of citizen scientists in modern astronomy. Instruments like SOHO and ATLAS generate vast datasets, but it is the human eye trained to notice anomalies that turns noise into discovery. Similarly, the confirmation of 3I Atlas's interstellar status relied on global networks of telescopes, from the Nordic Optical Telescope to the James Webb Space Telescope. This synergy between professionals and amateurs democratizes science, proving that the cosmos is accessible to all who dare to look. Yet these discoveries also reveal the limitations of our tools. The SWAN camera's low resolution delayed the precise tracking of C2025F2, while 3I Atlas's faintness in dense star fields near the galactic center obscured it from earlier detection. Such challenges remind us that the universe is vast, and our instruments, though powerful, are still imperfect lenses through which we peer into the unknown. Many comets, especially interstellar ones, may pass undetected, their icy nuclei vanishing into the void before humanity can glimpse them. Comets like C2025F2 and C2025R2 offer lessons in fragility and resilience. Their disintegration or survival under the sun's relentless heat mirrors the precarious balance of life on Earth. Yet their ability to traverse millions of kilometers and endure solar storms speaks to the durability of matter. For 3I Atlas, its interstellar journey is a reminder that the cosmos is a shared space, where objects from distant stars occasionally cross paths with our own. Its ancient age and alien chemistry challenge our understanding of planetary formation, suggesting that the building blocks of life may be scattered across the galaxy. Moreover, the study of cometary orbits reveals the gravitational ballet that governs the solar system. While C2025R2's 1400 to 20,000 year orbit hints at a distant past in the Oort cloud, 3I Atlas's hyperbolic path declares its origin beyond our stellar neighborhood. These trajectories are cosmic fingerprints, etched by the gravitational tugs of planets and the unseen forces of dark matter. By mapping them, we gain insight into the solar system's architecture and the likelihood of future interstellar visitors. To observe a comet is to confront the impermanence of existence. C2025F2's disintegration and 3I Atlas's departure into the void are metaphors for the transient nature of all things. Yet their legacies endure in data, in the memories of those who witnessed them, and in the questions they inspire. What might these comets have witnessed in their lifetimes? Did 3I Atlas once orbit a dead star, its surface sculpted by the winds of a dying sun? Could the molecules it carried seed the potential for life in another system? These questions stretch the limits of our imagination, yet they are grounded in science. Comets are not just icy rocks, they are time capsules, preserving the chemical history of their birthplaces. In studying them, we are in a sense reading the diary of the universe. And as we track their paths from the dusty corridors of SOHO to the pristine data of the James Webb Space Telescope, we are reminded that the cosmos is a story without end, written in light, gas, and the silent language of motion. With these comets now etched into our collective memory, we turn to the question that binds their fates. Why do some comets return, while others vanish into the void? The answer lies in their orbits, the invisible threads that stitch them to the sun and the planets. C2025F2's nearly parabolic path, 3I Atlas's hyperbolic escape, and C2025R2's long-period ellipse are more than mathematical curves. They are narratives of gravitational influence, cosmic encounters, and the inexorable pull of entropy. In the next segment, we will delve into the mechanics of cometary orbits, exploring how these delicate balances shape the destiny of each traveler. We will ask, what determines whether a comet becomes a periodic visitor or a one-time specter? How do planetary interactions alter their trajectories? And what do these orbits tell us about the solar system's past and its future? But for now, let us linger in the quiet awe of these celestial messengers. For every comet that fades from view, another may rise, carrying with it the promise of new discoveries. The universe, vast and unknowable, continues to invite us to listen to the whispers of ice and dust, to the echoes of distant stars, and to the infinite dance of creation and decay. Word count: 3,000 words, excluding headings and formatting. Tone: contemplative, scientific, poetic structure. Introduction: 1 paragraph. Explanation: 3 subsections. Exploration: 3 subsections. Transition: 1 paragraph. Key themes: cosmic interconnectedness, the role of human curiosity, the fragility and resilience of comets, the philosophical implications of interstellar travel. The universe is a vast tapestry of motion, where every object follows a path etched by the invisible hand of gravity. Comets, those ancient wanderers of the solar system, trace arcs through the void, their trajectories revealing secrets of their origins and destinies. Among the countless comets that have ever been observed, 2 stand out in 2025 for the stark contrast in their fates. See 2025 R2 SWAN and 3I Atlas. One dances along a delicate loop, bound to the sun's embrace, while the other rockets on a one-way journey, escaping the solar system forever. Their stories are written in the geometry of their orbits, parabolic curves that promise return, and hyperbolic escapes that signify farewell. To understand these comets is to glimpse the grand scale of the cosmos, where even fleeting visitors carry echoes of distant stars and the passage of eons. Orbits are not merely mathematical abstractions. They are the lifeblood of celestial navigation, the silent symphony of gravitational forces shaping the dance of worlds. For C 2025 R2, its path is a precarious ellipse, a fragile balance between the sun's pull and the comet's momentum. For 3I Atlas, its trajectory is a razor-sharp hyperbola, a cosmic exodus that defies the sun's grip entirely. These 2 comets offer a dual lens through which to explore the nature of motion in the universe, one bound by the laws of return, the other by the freedom of escape. Their stories are not isolated. They are threads woven into the fabric of galactic history, connecting our solar system to the wider expanse of interstellar space. To unravel these tales, we must first grasp the fundamental principles that govern orbital mechanics. Why do some comets return, while others vanish into the depths of the galaxy? How do the shapes of their paths, ellipses, parabolas, and hyperbolas, encode their origins and fates? In the following exploration, we will decode the language of orbits, using the contrasting journeys of C 2025 R2 and 3I Atlas as our guide. Through their stories, we will uncover the hidden architecture of the cosmos, where gravity is both a prison and a passport, and where the fate of a comet is sealed the moment it enters the solar system. The orbits of comets are governed by the same universal laws that dictate the motions of planets, asteroids, and even galaxies. At the heart of this cosmic choreography lies Newton's law of universal gravitation, which states that every mass attracts every other mass, with a force proportional to their product and inversely proportional to the square of the distance between them. When applied to a comet and the Sun, this law gives rise to 3 possible orbital paths: ellipses, parabolas, and hyperbolas. Each corresponds to a distinct relationship between the comet's kinetic energy and the gravitational potential energy exerted by the Sun. An elliptical orbit with an eccentricity e(1) is a closed curve forming a looping path that returns the comet to its point of origin. Most comets in the solar system follow such orbits, often stretching from the Kuiper belt or Oort cloud to the inner solar system and back. These comets are bound to the Sun, their trajectories dictated by the delicate balance between their forward velocity and the Sun's gravitational pull. For example, C 2025 R2 SWAN follows an elliptical orbit with a perihelion of 0.5 astronomical units, AU, just over half the distance between Earth and the Sun. Its aphelion, however, remains uncertain due to limited observational data, but preliminary estimates suggest it may extend to hundreds or thousands of years before returning. Such comets are ephemeral guests, their appearances fleeting reminders of the solar system's dynamic history. In contrast, a hyperbolic orbit with ESI 1 is an open curve, resembling a sharp, elongated arc that does not close. Objects on such trajectories possess sufficient velocity to overcome the sun's gravitational pull entirely, escaping the solar system and vanishing into interstellar space. The defining feature of a hyperbolic orbit is the escape velocity, the minimum speed required for an object to break free from a gravitational field. For the Sun, this velocity is approximately 617.5 kilometers per second at the distance of Earth. Any object exceeding this threshold will follow a hyperbolic path, never to return. 3I Atlas, the third confirmed interstellar comet, exemplifies this phenomenon. With an orbital eccentricity of 6.1414, the highest recorded for any solar system object, it entered the solar system at a velocity of 58 kilometers per second, far surpassing the Sun's escape velocity. This extraordinary speed ensures that 3I Atlas will not linger. It will pass through the inner solar system, skim the orbits of Mars and Venus, and then flee back into the void, carrying with it the chemical signatures of its alien birthplace. Between these extremes lies the parabolic orbit, SWAN, a theoretical boundary case where an object's velocity exactly matches the escape velocity. In practice, perfect parabolic orbits are rare, as minor perturbations from planets or other celestial bodies often nudge an object toward a slightly elliptical or hyperbolic path. However, many comets exhibit orbital characteristics close to parabolic, suggesting they originate from the distant reaches of the solar system, where gravitational influences are minimal. The C2025 F2 SWAN comet, though not directly relevant to this segment, provides a textbook example of such a trajectory, its nearly parabolic path hinting at an 80,000-year orbital period and a journey from the outer Oort cloud. The distinction between these orbital types is not merely academic. It is a window into the origins of comets. Elliptical orbits imply a native connection to the solar system, while hyperbolic trajectories signal interstellar provenance. The eccentricity of an orbit acts as a cosmic fingerprint, revealing whether a comet is a transient visitor from the Kuiper belt or a long-lost wanderer from another star system. For 3I Atlas, this fingerprint is unmistakable. Its hyperbolic escape velocity and retrograde inclination place it firmly in the category of interstellar objects, while C2025 R2's elliptical path anchors it to the solar system's gravitational web. Yet the story of their orbits is more than a matter of geometry. It is a chronicle of motion and time. The perihelion distance of a comet determines how close it ventures to the Sun, exposing it to intense heat and radiation that can trigger dramatic outbursts or even disintegration. C2025 R2's perihelion, at 0.5 AU, places it in a perilous zone, where solar radiation can strip away volatile ices and fragment its nucleus. Conversely, 3I Atlas's perihelion at 1.36 AU, while still within the inner solar system, spares it the most extreme conditions, allowing it to retain its icy composition as it hurtles outward. These differences in proximity shape the comet's fates. One may end its journey in a spectacular explosion of dust and gas, while the other will vanish quietly, a ghostly traveler leaving no trace but its trajectory. The orbits of C2025 R2, SWAN, and 3I Atlas are more than mere pathways through space. They are records of their histories, encoded in the mathematics of motion. To decipher these records, astronomers analyze the velocity components of comets as they enter the solar system, breaking them down into radial, transverse, and vertical vectors relative to the Milky Way's galactic center. For 3I Atlas, this analysis reveals a startling truth. Its trajectory suggests it originated from the galactic thick disk, a spherical halo of ancient stars surrounding the galaxy's plane. The thick disk is a repository of the Milky Way's earliest stars, many of which formed billions of years before the Sun. If 3I Atlas hails from this population, it could be 7 to 14 billion years old, older than the solar system itself. Such an age would make it a relic from the galaxy's formative years, a time when stars were young and the interstellar medium was rich with the raw materials of life. This conclusion is supported by 3I Atlas's vertical velocity component, Watts-Ponce 18.5 kilometers per second, which indicates it is moving upward through the galactic plane. Unlike the flat disk-like orbits of most solar system objects, 3I Atlas's tilted trajectory aligns it with the thick disk's population of older stars. These stars, born in the turbulent youth of the galaxy, have compositions depleted in heavy elements compared to younger stars like the Sun. The chemical makeup of 3I Atlas, rich in carbon dioxide and containing traces of cyanide and nickel, may reflect this primordial heritage. By studying such interstellar comets, astronomers gain access to the building blocks of distant star systems, offering a rare glimpse into the chemistry of the early universe. Meanwhile, C2025R2, SWAN's elliptical orbit, tells a different story. Though its exact origin remains uncertain, its perihelion and aphelion suggest it may originate from the inner Oort cloud, a distant reservoir of icy bodies influenced by the gravitational tugs of passing stars and the galactic tide. The Oort cloud is a hypothesized shell of trillions of comets, extending up to 100,000 AU from the Sun. Occasionally, external forces perturb these objects, sending them spiraling inward on long-period orbits. C2025R2 is likely one such wanderer, ejected from the Oort cloud millions or billions of years ago, and only now returning to the inner solar system. Its orbital period, estimated at 1,400 to 20,000 years, underscores the vast timescales over which cometary dynamics unfold. The implications of these findings extend beyond individual comets. 3I Atlas's interstellar origin challenges assumptions about the distribution of rogue objects in the galaxy. While previous interstellar visitors, such as 1I Oumuamua and 2I Borisov, were expected to originate from the solar apex, the direction of the Sun's motion through the galaxy, 3I Atlas arrived from the southern celestial hemisphere, a region previously considered less likely to host detectable interstellar objects. This discrepancy suggests that southern origin interstellar comets may be more common than models predict, or that observational biases have skewed our understanding of their distribution. Either way, 3I Atlas serves as a reminder that the galaxy is a dynamic, interconnected web of motion, where objects from distant star systems occasionally cross paths with ours. For C2025R2, the stakes are equally profound. Its close approach to Earth 0.26 AU raises the possibility of a meteor shower when Earth crosses its orbital path in October 2025. While no meteor storm is expected, the event highlights the role of comets as cosmic couriers, scattering debris that can be studied for insights into their composition and history. Meteor showers are, in essence, the aftermath of cometary journeys, their particles remnants of ancient collisions and outgassing events. By analyzing these fragments, scientists can reconstruct the conditions under which comets formed, shedding light on the processes that shape the solar system. Yet the most compelling aspect of these comets is their temporal scale. 3I Atlas, if 7 billion years old, predates the solar system by over twice its current age. It has traveled across the galaxy for epochs measured in millions of years, surviving encounters with stars and nebulae, before finally crossing our cosmic neighborhood. Its brief visit to the inner solar system is a fleeting moment in its long journey, a chance encounter that may never recur. Similarly, C2025R2's return, should it complete its 1,400 to 20,000 year orbit, will not occur for millennia, a testament to the patience required to witness the full cycle of a comet's life. These comets also underscore the interconnectedness of the universe. The Sun's gravitational influence extends far beyond the planets, drawing in objects from the Oort cloud, and occasionally from interstellar space. In turn, the solar system acts as a conduit, dispersing material, comets, asteroids, and even ejected planets into the galactic expanse. The arrival of 3I Atlas is not an anomaly, but a natural consequence of this cosmic exchange, a reminder that no star system exists in isolation. The orbits of C2025R2, SWAN, and 3I Atlas are cosmic fingerprints, etched by the hands of gravity and time. Yet these paths are only part of the story. To truly understand these comets, we must look deeper into the very substance of their being. What lies beneath their surfaces? What volatile ices and organic compounds hide within their nuclei? How do their compositions reflect their origins? And what do they tell us about the formation of the solar system and the galaxy? The answers lie in the chemical signatures left behind in their comas and tails. As comets approach the Sun, heat sublimates their ices, releasing gases and dust that form the glowing halos and sweeping tails that make them visible to Earth. These emissions are not random. They are the products of a comet's history, forged in the cold crucible of the outer solar system, or the alien chemistry of another star system. For 3I Atlas, its unusual richness in carbon dioxide and its detection of cyanide and nickel hint at a composition unlike any native comet, offering a glimpse into the chemistry of interstellar space. For C-2025-R2, the question remains, will its fragile nucleus withstand the sun's fury, or will it disintegrate, scattering its secrets into the void? In the next segment, we will embark on a journey to the heart of these comets, exploring their nuclei, ices, and the molecules that bind them. We will uncover the role of comets as time capsules, preserving the building blocks of life and the echoes of distant stars. And we will ask, what do these frozen relics reveal about our own origins, and about the universe that gave rise to them? The universe is a vast, enigmatic expanse where time stretches beyond human comprehension, and the remnants of ancient epochs drift silently through the void. Among these celestial wanderers, comets stand as frozen relics, preserving the chemical signatures of their birthplaces. They are more than mere streaks of light in the night sky. They are cosmic messengers, carrying stories of distant star systems and the primordial chaos of planetary formation. As we peer into the icy hearts of comets like 3I Atlas and C-2025-R2 SWAN, we are not merely observing transient phenomena. We are deciphering the molecular blueprints of worlds long gone and galaxies yet to be born. The discovery of 3I Atlas, the third confirmed interstellar visitor to our solar system, has opened a window into the chemistry of alien star systems. Unlike the countless comets that originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas hails from interstellar space, hurtling through the solar system with a hyperbolic trajectory that defies gravitational capture. Its journey is a testament to the dynamic nature of the cosmos, where rogue objects are flung from their homes by the gravitational tides of distant stars. Meanwhile, C-2025-R2 SWAN, though bound to our Sun, offers its own mysteries, a volatile nucleus that brightens and disintegrates, revealing the fragility of these icy bodies when subjected to the relentless heat of the Sun. Together, these comets serve as cosmic time capsules, their compositions whispering secrets about the origins of planetary systems, the evolution of star clusters, and the fundamental building blocks of life itself. To understand comets is to trace the threads of cosmic history woven through the fabric of the universe. Every grain of dust and molecule of gas they release tells a story of cold, distant reservoirs, where ice is formed in the shadows of young stars. Spectroscopy, the analytical tool that breaks down light into its constituent wavelengths, allows scientists to decode these stories. By examining the spectral fingerprints of cometary material, researchers can identify the presence of water, carbon dioxide, complex organic molecules, and even metals like nickel. These discoveries do not merely catalogue the ingredients of a comet, they illuminate the shared heritage of planetary systems and the universal processes that govern their formation. In the case of 3I Atlas, its chemical composition bears striking similarities to comets within our own solar system, yet subtle differences hint at a history shaped by the unique conditions of its interstellar home. As we delve deeper into the chemical makeup of these comets, we are confronted with profound questions. Are the processes that forged our solar system mirrored in the far reaches of the galaxy? What can the age and origin of 3I Atlas reveal about the evolution of the Milky Way? And what does the volatile fate of C-2025-R2 SWAN tell us about the resilience or fragility of cometary nuclei in the face of solar radiation? These inquiries are not confined to the realm of theoretical astronomy. They are grounded in the meticulous observations of instruments like the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories that track the fleeting trajectories of these icy travelers. Each new data point brings us closer to unraveling the cosmic tapestry that binds the stars, planets, and comets into a singular, interconnected narrative. The composition of a comet is a direct reflection of its place of origin, shaped by the temperatures, pressures, and chemical environments of its birthplace. Within our solar system, comets from the Oort cloud and Kuiper Belt typically contain a mix of water ice, carbon dioxide, methane, ammonia, and complex organic molecules such as cyanide compounds and hydrocarbons. These materials froze into solid forms in the frigid outer reaches of the protoplanetary disk that gave rise to the Sun and planets. When a comet ventures closer to the Sun, solar radiation begins to sublimate these ices, releasing gases and dust that form the comet's coma and tail. The resulting spectroscopic signature, a unique pattern of absorption and emission lines in the electromagnetic spectrum, allows astronomers to identify the specific molecules present in the comet's atmosphere. 3I Atlas presents a particularly intriguing case, as its interstellar origin necessitates a comparison with the chemistry of comets from entirely different stellar nurseries. Observations by the James Webb Space Telescope, JWST, have revealed that 3I Atlas is unusually rich in carbon dioxide, a finding that contrasts with the more water-dominant composition of many solar system comets. While water ice is still present in its coma, the proportion of carbon dioxide is significantly higher, suggesting that the comet may have formed in an environment where temperatures were colder or where the chemical equilibrium favored the preservation of CO2. Additionally, spectroscopic analyses have detected traces of water vapor, carbon monoxide, and carbonyl sulfide, all of which contribute to the comet's overall activity. More surprisingly, the Very Large Telescope, VLT, has identified the presence of cyanide gas and atomic nickel vapor in 3I Atlas's coma elements that, while not unheard of in solar system comets, are observed at concentrations that challenge existing models of cometary chemistry. C 2025 R2, SWAN, in contrast, exhibits a more volatile-driven behavior, discovered by the solar and heliospheric observatories. Mausho SWAN instrument. This comet has undergone a rapid brightening phase as it approached the Sun, a phenomenon often linked to the sublimation of volatile ices, such as carbon dioxide, methane, and ammonia. Its sudden increase in brightness from magnitude 11 to 6.9 in a matter of weeks suggests that the comet is composed of a nucleus rich in these easily evaporated substances. The presence of a tail measuring up to 2 degrees in length further supports the idea of a volatile-rich composition, as the tail is primarily composed of ionized gases and fine dust particles released during the sublimation process. However, unlike some comets that maintain their integrity despite intense solar heating, C 2025 R2 appears to be disintegrating. This fragmentation is likely the result of thermal stresses and the loss of structural cohesion as its volatile components escape into space. The comet's fate is a reminder of the delicate balance between stability and destruction that governs the lives of these icy wanderers. The study of cometary composition is not merely an academic exercise, it is a key to unlocking the history of planetary systems. The presence of certain molecules in a comet's coma can indicate the temperature at which it formed, the chemical processes that occurred in its parent star's protoplanetary disk, and even the likelihood of habitable conditions in its native system. For instance, the detection of water ice in 3I Atlas raises questions about the distribution of water in the galaxy and the possibility that it played a role in the development of life in distant star systems. Similarly, the presence of complex organic molecules in both 3I Atlas and C 2025 R2 suggests that the building blocks of life may be more widespread than previously thought. These findings reinforce the idea that comets are not just frozen debris, they are cosmic archives, preserving the chemical imprints of the earliest moments in planetary formation. The similarities between 3I Atlas and solar system comets suggest that the processes governing the formation of planetary systems may be more universal than once imagined. Despite originating from a distant star system, 3I Atlas shares key chemical traits with comets from our own backyard. Its coma contains water ice, carbon dioxide, and complex organic molecules, all of which are commonly observed in comets such as Halley's Comet and 67P Churyumov-Gerasimenko. This striking resemblance implies that the fundamental mechanisms responsible for the creation of comets, namely, the condensation of volatile ices in the cold outer regions of a protoplanetary disk, are not unique to our solar system. Instead, they appear to be a recurring theme in the cosmic drama of planetary birth, playing out in the cradles of distant stars. The fact that 3I Atlas's composition mirrors that of solar system comets reinforces the notion that the same physical and chemical principles operate across the galaxy, shaping the architecture of planetary systems regardless of their location. Yet for all its similarities, 3I Atlas also possesses a quality that sets it apart: its extraordinary age. Based on its trajectory and velocity components, astronomers estimate that the comet is between 3 and 14 billion years old, placing it in the same temporal range as the oldest stars in the Milky Way. This revelation has profound implications for our understanding of galactic evolution. If 3I Atlas indeed dates back to the early days of the Milky Way, it may have formed in a vastly different environment, one where the galactic disk was still coalescing, and where the abundance of heavy elements was far lower than it is today. Such an origin would mean that 3I Atlas is not merely a visitor from another star system. It is a relic from a time when the galaxy was young, carrying with it the chemical imprints of an era long since transformed. Studying this interstellar wanderer offers a rare opportunity to peer into the past, to glimpse the conditions that prevailed in the early Milky Way, and to understand how planetary systems evolve over billions of years. The implications of 3I Atlas's advanced age extend beyond the realm of galactic history. If the comet is truly older than the solar system, it challenges our assumptions about the timescales of planetary formation and the longevity of cometary bodies. Most comets within our solar system are believed to be only a few billion years old, having survived the chaotic early stages of the solar system's formation and remaining preserved in the Oort cloud or Kuiper belt. However, 3I Atlas's journey through interstellar space suggests that comets can persist for much longer periods, surviving the gravitational perturbations of distant stars and the harsh conditions of the galactic void. Its survival over such an immense timespan raises intriguing questions about the resilience of cometary nuclei and the mechanisms that allow them to endure. Did 3I Atlas form in a particularly stable region of its parent star system, shielded from disruptive forces? Or did it originate from a different kind of protoplanetary disk, one that produced comets with unique structural properties? These uncertainties highlight the gaps in our understanding of cometary evolution and underscore the importance of continued observations of interstellar visitors like 3I Atlas. Moreover, the discovery of 3I Atlas opens a new frontier in the search for extraterrestrial life. The presence of water ice, complex organic molecules, and even trace amounts of cyanide in its coma suggests that the building blocks of life may be more common in the universe than previously thought. If comets like 3I Atlas routinely carry these essential ingredients, it strengthens the hypothesis that life-sustaining materials could be delivered to planets across the galaxy, potentially seeding the emergence of life in distant star systems. This idea aligns with the theory of panspermia, which posits that microbial life or its precursors may have been transported between planets via comets or asteroids. While the existence of life on 3I Atlas itself remains speculative, the comet's chemistry serves as a compelling reminder that the conditions necessary for life may be far more widespread than we ever imagined. As the scientific community continues to analyze the data from 3I Atlas and other interstellar comets, one thing becomes increasingly clear: comets are not just transient objects, they are cosmic time capsules, preserving the history of planetary formation and the chemical evolution of the galaxy. Whether they originate from within our solar system or from the depths of interstellar space, these icy wanderers offer invaluable insights into the processes that shape the universe. In the case of 3I Atlas, its journey through the solar system is a fleeting moment in the grand cosmic timeline, but the knowledge it imparts will resonate for generations to come. Through its spectral fingerprints and its ancient lineage, 3I Atlas reminds us that the universe is a vast and interconnected web of history, where every comet that passes through the heavens carries a piece of the story that binds us all together. As these comets draw closer to the sun, their fragile structures begin to unravel, revealing the transformative power of solar energy. The warmth of the sun, a force that has sculpted the surfaces of planets and driven the evolution of the solar system, now turns its attention to these icy travelers. For 3I Atlas, the interstellar intruder, and C2025 R2 SWAN, the volatile wanderer of our own solar system, the sun's embrace is both a source of illumination and a harbinger of change. The question that arises is not just how they will behave under the sun's influence, but what these transformations can teach us about the nature of comets, the limits of their endurance, and the cosmic forces that govern their fates. The sun's rays, composed of electromagnetic radiations, spanning from infrared to ultraviolet, strike the comet's surfaces, initiating a cascade of physical and chemical reactions. Volatile ices, water, carbon dioxide, methane, and ammonia begin to sublimate, transitioning directly from solid to gas without passing through a liquid phase. This process not only releases a mixture of gases and dust, but also accelerates the erosion of the cometary nucleus, often leading to fragmentation or complete disintegration. The intensity of these effects depends on the comet's composition, its proximity to the Sun, and the structural integrity of its nucleus. For C-2025 R2 SWAN, which has already exhibited signs of instability, the Sun's heat may hasten its demise, reducing it to a cloud of dust and gas that will dissipate into the solar system's vast expanse. Conversely, 3I Atlas, with its interstellar origins and perhaps a denser, more resilient nucleus, may withstand the solar onslaught for a longer duration, offering scientists a rare opportunity to study an interstellar object under extreme conditions. The coming chapters of these comets' journeys will unfold against the backdrop of the Sun's gravitational dominance and radiant energy. What awaits them is a final act of cosmic transformation, one that will either mark their end or reveal the full extent of their resilience. As we turn our gaze toward the Sun, we prepare to witness the ultimate test of a comet's survival, where the line between destruction and revelation blurs. How will these icy wanderers respond to the Sun's inexorable pull? What secrets will their final moments unveil? The answers lie ahead, waiting to be uncovered as the comets approach their closest encounters with the heart of the solar system. The Sun, a blazing heart at the center of our cosmic neighborhood, is both a sculptor and a harbinger of transformation. Its radiant energy, a force of creation and destruction, governs the fate of comets as they traverse the vastness of space. These icy wanderers, born in the frigid outskirts of planetary systems, are drawn toward the Sun's gravitational embrace, where their journeys take on a dramatic crescendo. For every comet that survives the inferno of solar proximity, there are countless others that disintegrate, their fragile nuclei shattered by the relentless pull of heat and light. The Sun's influence is not merely a passive force. It is an architect of change, reshaping comets in ways that reveal the delicate balance between existence and oblivion. Among the many comets that have graced human observation in recent years, two stand out as exemplars of this cosmic dance: C-2025 F2 SWAN and 3I Atlas. While SWAN, a native of our solar system, met a tragic end as it spiraled toward its fiery demise, 3I Atlas, an interstellar traveler from distant realms, continues its voyage unscathed. Their stories, though divergent, are threads woven into the same tapestry of celestial mechanics. They remind us that the Sun is not merely a backdrop to the drama of the cosmos, but an active participant in the lives of these ephemeral visitors. Whether it is the sudden outbursts that precede a comet's disintegration, or the silent sublimation of ices that fuels its luminous coma, the Sun's touch is both inevitable and profound. Yet the Sun's role extends beyond the visible spectacle of tails and halos. It is a laboratory of extremes, where the fundamental nature of cometary material is laid bare. The heat that drives the transformation of ice into gas, the pressure that shapes the delicate filaments of dust, and the radiation that strips away layers of volatile compounds, all are manifestations of the Sun's power. To understand comets is to understand the Sun, for they are inseparable partners in a cosmic ballet that spans millennia. As we peer into the histories of SWAN and 3I Atlas, we are not merely observing the trajectories of distant objects. We are witnessing the Sun's enduring influence on the fabric of the solar system itself. When a comet ventures too close to the Sun, it undergoes a metamorphosis that is as violent as it is beautiful. The process begins with sublimation, the direct transformation of solid ice into gas without passing through the liquid phase. This occurs when solar radiation penetrates the comet's surface, heating the frozen reservoirs of water, carbon dioxide, methane, and other volatile compounds embedded within its nucleus. As these ices warm, they release clouds of gas that envelop the nucleus in a glowing envelope called the coma. The coma, often spanning thousands of kilometers in diameter, is a dynamic and ever-changing structure, constantly replenished as more material is stripped from the comet's interior. Simultaneously, the solar wind, a stream of charged particles emanating from the Sun's corona, interacts with the coma, giving rise to the ion tail. Unlike the coma, which is composed of neutral gas and dust, the ion tail is composed of electrically charged particles that are pushed directly away from the Sun by magnetic forces. This tail, always pointing radially outward, is distinct from the dust tail, which curves gently in the direction of the comet's motion due to the combined effects of solar radiation pressure and the comet's orbital velocity. Together, these tails create the iconic appearance of a comet, a celestial arrowhead pointing toward the Sun's heart. However, the Sun's influence is not always benign. For comets like C2025 F2, SWAN, the journey toward perihelion, the point of closest approach to the Sun, is marked by instability. SWAN's rapid brightening in early April 2025, followed by its sudden dimming and disintegration in late April, underscores the fragility of these objects. The outburst observed during its brief moment of brilliance suggests that the nucleus was unable to withstand the escalating pressures of sublimation. As volatile gases expanded within the porous structure of the nucleus, internal stresses mounted until the comet fractured, scattering its remnants into a diffuse cloud of dust and debris. This disintegration was not an anomaly, but a testament to the Sun's capacity to dismantle even the most resilient comets. In contrast, 3I Atlas, the interstellar visitor, exhibits a remarkable resilience to solar heating. Its trajectory, defined by a hyperbolic excess velocity of 58 kilometers per second, ensures that it will not remain within the solar system for long. Yet, as it approaches its perihelion at 1.36 AU in October 2025, the Sun's influence is evident in the comet's activity. Observations by the James Webb Space Telescope, JWST, have revealed that 3I Atlas's Comet is rich in carbon dioxide, a molecule that sublimates at lower temperatures than water ice. This suggests that the comet's activity is primarily driven by CO2, allowing it to remain active even at distances where water-based comets might falter. The presence of CO2 also hints at the comet's possible origin in a colder, more distant region of its home system, where such volatile compounds could have remained frozen for eons. The Sun's role in shaping cometary activity is further underscored by the variability observed in their brightness and structure. For example, SWAN's outburst in early April 2025, which temporarily boosted its apparent magnitude from 10.6 to 8.6, was likely triggered by a localized release of volatile material. Such events, though fleeting, provide valuable insights into the internal composition and structural integrity of comets. Similarly, the evolving color and composition of 3I Atlas's Comet, as observed by ground-based and space-based telescopes, reflect the complex interplay between solar heating and the comet's chemical makeup. The reddening of its coma over time, for instance, indicates the presence of organic molecules or fine-grained silicates that absorb blue light preferentially. These observations not only illuminate the life cycle of individual comets, but also offer clues about the conditions in their birthplaces, whether within the solar system or beyond. What distinguishes the Sun's influence on comets is its universality. Regardless of their origin, whether from the Oort cloud, the scattered disk, or an alien star system, the laws governing their interaction with solar radiation remain constant. The sublimation of ices, the formation of comae and tails, and the eventual disintegration or fragmentation of nuclei are all manifestations of the same physical principles. This universality allows scientists to draw parallels between comets within our solar system and those that originate elsewhere, bridging the gap between familiar and foreign worlds. Through the lens of the Sun, we see not just the fate of individual comets, but the overarching patterns that govern the evolution of celestial bodies across the galaxy. The Sun's role in shaping cometary activity extends beyond the immediate spectacle of their passage through the inner solar system. It offers a window into the broader processes that dictate the longevity and survival of these objects. For comets like C2025 F2 SWAN, the Sun's relentless energy acts as a double-edged sword. On one hand, it ignites the transformation of ice into gas, creating the luminous coma and tails that define a comet's identity. On the other, it accelerates the erosion of the nucleus, often leading to catastrophic disintegration. SWAN's fate, marked by its sudden outburst and subsequent dissolution, serves as a stark reminder that not all comets are built to endure the trials of solar proximity. Its brief moment of brilliance, captured in images and spectra, is a poignant testament to the fragility of these icy wanderers. In contrast, the resilience of 3I Atlas highlights the adaptability of comets in the face of extreme conditions. Its ability to maintain activity despite its rapid trajectory and high hyperbolic excess velocity suggests a composition and structure uniquely suited to interstellar travel. The abundance of carbon dioxide in its coma, for instance, implies that the comet may have originated in a region of its home system where temperatures were low enough to preserve such volatile compounds. This insight not only deepens our understanding of 3I Atlas's origins, but also sheds light on the diversity of environments in which comets can form. If 3I Atlas indeed hails from the Milky Way's thick disk, a population of ancient stars with lower metallicity than the Sun, its survival could indicate that comets from such regions possess distinct chemical and structural properties. These findings challenge assumptions about the uniformity of cometary materials and underscore the importance of studying interstellar visitors to broaden our knowledge of planetary formation beyond our own system. Moreover, the Sun's influence on cometary activity has profound implications for our understanding of the cosmic timeline. The fact that 3I Atlas may be as old as 7.6 to 14 billion years, far older than the solar system itself, raises intriguing questions about the longevity of cometary nuclei. If a comet can survive for such an extended period in the interstellar void, it suggests that some comets are not merely transient visitors, but relics of the earliest epochs of the galaxy. The preservation of these ancient objects, even as they traverse the hostile environment of the inner solar system, hints at the robustness of certain materials against the erosive forces of time and energy. Such discoveries compel us to reconsider the role of comets as cosmic time capsules, carrying within them the signatures of conditions that existed billions of years ago. The disintegration of SWAN, on the other hand, underscores the ephemeral nature of many comets. While its lifespan may be measured in centuries or millennia, the final act of its journey, its collapse into a cloud of dust and debris, occurs in mere days. This rapid transformation is not uncommon among comets, particularly those with weakly consolidated nuclei or high porosity. The Sun's role in accelerating this process is both a creative and destructive force, sculpting the comet's final moments into a fleeting display of light and shadow. Observing such events provides invaluable data on the mechanical properties of cometary nuclei, revealing how they respond to stress and thermal gradients. These insights, in turn, inform models of comet evolution and help refine predictions about future cometary encounters. Beyond their individual stories, the fates of SWAN and 3I Atlas contribute to a larger narrative about the dynamic equilibrium of the solar system. The Sun's gravitational dominance ensures that comets are either captured into long-period orbits or ejected into interstellar space, their paths dictated by the delicate balance of energy and momentum. Those that survive the encounter become part of the solar system's extended family, while those that disintegrate or escape leave behind only traces of their existence. This cycle of arrival, transformation, and departure is a continuous process, one that shapes the distribution of comets and influences the likelihood of future encounters. The study of these interactions not only enriches our understanding of cometary behavior, but also enhances our ability to anticipate and prepare for the next great visitor from the cosmos. Perhaps most significantly, the Sun's role in cometary activity bridges the gap between the familiar and the unknown. By examining how comets respond to solar heating, we gain insights into the physical and chemical processes that govern not only their evolution, but also the formation of planetary systems. The presence of carbon dioxide in 3I Atlas's coma, for example, mirrors the volatile rich environments of the outer planets and their moons, suggesting that the building blocks of such worlds may share a common heritage with interstellar comets. Similarly, the structural weaknesses that led to SWAN's disintegration offer a glimpse into the internal architecture of comets, revealing how they differ from asteroids and other minor bodies. These comparisons are essential for unraveling the mysteries of planetary formation and migration, as they highlight the diverse pathways by which celestial objects acquire their defining characteristics. As we reflect on the Sun's transformative power over comets, a lingering question emerges: how do we track these celestial wanderers, especially when they vanish into the Sun's blinding glare? The answer lies not only in the instruments we build, but in the ingenuity of the minds that wield them. From the vantage of space-based observatories to the meticulous calculations of orbital mechanics, the pursuit of comets requires a blend of precision and imagination. Yet, even with these tools, the challenge remains formidable. How do we follow an object that is both too faint and too close to the Sun? What techniques allow us to detect comets before they emerge from the darkness of space? And how do we ensure that no visitor, no matter how fleeting, escapes our gaze? These questions lead us to the heart of the next chapter in our exploration: the art and science of comet detection. The methods employed to uncover these elusive travelers are as varied as the comets themselves, ranging from wide-field surveys that scan the skies for subtle changes in light, to specialized instruments designed to pierce the veil of solar radiation. Each technique is a testament to humanity's determination to map the unseen, to find order in the chaos of the cosmos. As we turn our attention to the tools and strategies that enable these discoveries, we step into a realm where technology meets curiosity, where the limits of observation are pushed ever further in the quest to understand the universe. The next segment will illuminate the intricate web of efforts that keep our eyes fixed on the heavens, ensuring that no comet, no matter how brief its journey, goes unnoticed. In the vast expanse of the cosmos, where light travels across eons to reach our eyes, the faintest whispers of celestial bodies often go unnoticed. Yet, among these elusive objects, comets hold a special place, a fleeting dance of ice and dust against the backdrop of eternity. To track a comet like C2025 R2 SWAN or 3I Atlas is to peer into the abyss, where the boundaries between the known and the unknown blur. These comets, born of distant stars and ancient voids, traverse the solar system with silent purpose, their paths etched by forces we barely comprehend. To observe them is to stand at the edge of knowledge, gazing into the infinite, with tools forged by human ingenuity. The challenge of tracking faint comets is as much philosophical as it is technical. Amper's comet at 15th magnitude is a ghostly apparition, a speck of light lost in the cosmic tapestry. Its faintness defies casual observation, demanding instruments capable of sifting signal from noise, of resolving a single grain of sand in a desert of stars. Why do these objects elude us? Because they exist at the margins of visibility, where the sun's glare drowns out their feeble glow, where the vast distances between worlds render even the most powerful telescopes insufficient. Yet humanity persists, driven by an insatiable curiosity to chart the unseen. From the vantage of Earth, we deploy arrays of adaptive optics to sharpen blurred images, launch space-based observatories to pierce atmospheric distortions, and rely on robotic networks to scan the heavens with tireless precision. Each detection is a triumph, a testament to our ability to wrest meaning from the void. But the pursuit of faint comets is not merely an exercise in technical prowess. It is a window into the grand design of the universe. Consider C2025 R2 SWAN, a celestial wanderer glimpsed only briefly before vanishing once more into the depths of space. Its discovery, made possible by the Solar and Heliospheric Observatory, MAUSHOHO SWAN instrument, underscores the fragility of our observations. For months, the comet remained hidden, its proximity to the sun rendering it invisible to ground-based telescopes. Only when it emerged from the shadows, its tail stretching 2 degrees across the night sky, did its existence become undeniable. Similarly, 3I Atlas, the third interstellar visitor to grace our solar system, defied expectations by arriving from the southern celestial hemisphere, an anomaly that reshaped our understanding of the distribution of interstellar objects. These comets are not mere curiosities, they are messengers from distant stars, carrying secrets of their birthplaces across the galactic expanse. To track such objects is to navigate a paradox. The more we learn, the more we realize how much remains hidden. The faintness of a comet is a mirror reflecting our own limitations, a reminder that the cosmos is vaster and stranger than we dare imagine. Yet it is precisely this uncertainty that fuels our quest. Every new discovery, every fleeting glimpse of a comet's tail, expands the frontiers of knowledge, pushing us closer to answering the timeless question, what lies beyond the veil of the observable universe? The ability to detect and track faint comets hinges on the sophistication of modern astronomical instrumentation, each tool designed to overcome the inherent challenges posed by their diminutive brightness. Ground-based observatories, equipped with advanced adaptive optics systems, play a crucial role in this endeavor. Adaptive optics correct for atmospheric distortion by using deformable mirrors that adjust in real time to counteract turbulence. This technology enables telescopes to achieve clarity akin to what they would experience in the vacuum of space, allowing astronomers to resolve the faint glimmers of comets like C2025 R2 SWAN when they emerge from the shadow of the sun. These systems are particularly vital for capturing detailed images of cometary nuclei, which are often shrouded in the haze of their surrounding coma. Space telescopes such as the Hubble Space Telescope and the James Webb Space Telescope, JWST, offer unparalleled advantages in observing faint comets. Free from the distorting effects of Earth's atmosphere, these instruments can capture high-resolution images and spectra that reveal intricate details of a comet's composition and structure. For instance, The Hubble's ultraviolet capabilities enable scientists to analyze the chemical makeup of a comet's coma, identifying gases and ices that evaporate as the comet approaches the Sun. The JWST, with its infrared sensitivity, complements these observations by detecting thermal emissions from cometary dust, providing insights into the temperature and distribution of material within the coma. These combined efforts allow astronomers to construct a comprehensive picture of a comet's behavior, even when its intrinsic brightness is minimal. Robotic observatories further enhance our capacity to track faint comets by automating the process of scanning the skies for transient phenomena. Networks like the Asteroid Terrestrial Impact Last Alert System, ATLAS, and the Zwicky Transient Facility, ZTF, operate continuously, employing algorithms to sift through vast amounts of data in search of subtle changes in the night sky. When a faint comet like 3I Atlas is detected, these systems can alert astronomers almost instantaneously, facilitating follow-up observations with larger telescopes. This rapid response is essential for capturing critical moments in a comet's journey, such as its perihelion passage or sudden outbursts of activity. Moreover, the unique observational constraints of individual comets necessitate tailored strategies. For C2025 R2 SWAN, which reaches a solar elongation of 30 degrees, the limited window of visibility requires careful planning. Observers must coordinate their efforts to maximize the chances of capturing the comet during its brief appearance, often utilizing telescopes positioned in the southern hemisphere where it is best seen. Conversely, 3I Atlas's trajectory, which brings it perilously close to the Sun, demands innovative solutions. During its solar conjunction phase, when it is obscured by the Sun from Earth's perspective, observations by Mars orbiters like NASA's Mars Reconnaissance Orbiter or the European Space Agency's ExoMars Tracegas Orbiter become invaluable. These spacecraft can provide data on the comet's activity as it approaches perihelion, filling in the gaps left by Earth-based observations. The integration of these diverse technologies not only enhances our ability to detect faint comets, but also deepens our understanding of their nature. By combining ground-based and space-based observations, astronomers can piece together a more complete narrative of a comet's life cycle, from its formation in the outer reaches of its home system to its dramatic encounter with the Sun. Each detection, whether it reveals a comet's disintegration or a sudden burst of activity, contributes to a broader tapestry of cosmic events, illuminating the dynamic processes that govern the universe. In this way, the tools of observation serve as both a means of discovery and a bridge between the known and the unknown, guiding us toward a deeper comprehension of the cosmos. The pursuit of faint comets extends beyond the immediate thrill of discovery. It fundamentally reshapes our understanding of the cosmos and the evolutionary trajectory of astronomical tools. These elusive objects, often born in the icy depths of distant star systems, serve as cosmic messengers that carry the imprints of their origins. By studying comets like C2025 R2 SWAN and 3I Atlas, we gain insight into the conditions of their respective stellar nurseries, offering clues about the diversity of planetary systems and the processes that govern their formation. For instance, the chemical composition of a comet's coma, rich in volatile substances such as water ice, carbon dioxide, and complex organic molecules, provides a snapshot of the primordial materials that once coalesced to form planets. Such findings challenge our assumptions about the uniformity of the universe, revealing a tapestry of environments where the building blocks of life may have originated in myriad ways. Moreover, the study of faint comets illuminates the dynamic interactions within the solar system itself. As these comets traverse their orbits, they interact with the gravitational forces of planets and the Sun, often leading to dramatic changes in their trajectories and appearances. The disintegration of C2025 F2 SWAN, for example, highlights the fragility of cometary nuclei under the intense heat and radiation of the Sun. Observing such events not only enhances our understanding of the physical properties of comets, but also informs models of how these bodies evolve over time. The data collected from these transient encounters contribute to our broader knowledge of the solar system's architecture, helping us to map the intricate web of gravitational influences that dictate the paths of celestial bodies. The evolution of astronomical tools in response to these challenges is equally profound. The development of advanced imaging technologies and data processing algorithms reflects a growing recognition of the need for precision in our observations. Instruments like the James Webb Space Telescope exemplify this trend, utilizing cutting-edge engineering to detect faint signals that were once beyond our reach. The integration of artificial intelligence in data analysis further enhances our capability to sift through vast data sets, identifying patterns and anomalies that might otherwise go unnoticed. As we refine our observational techniques, we not only improve our ability to track faint comets, but also expand the horizons of our scientific inquiry, enabling us to explore phenomena that were previously deemed inaccessible. This ongoing evolution of technology is poised to revolutionize the field of astronomy in the coming decades. Future observatories, such as the Vera C. Rubin Observatory, promise to usher in a new era of discovery by conducting wide-field surveys of the sky with unprecedented depth and frequency. These surveys will not only enhance our ability to detect faint comets, but also to identify other transient phenomena, such as supernovae and gamma-ray bursts, contributing to a more comprehensive understanding of the universe's dynamic nature. Furthermore, the anticipated launch of next-generation space telescopes will provide insights into the atmospheres of exoplanets, expanding our search for habitable worlds and the potential for life beyond our solar system. As we stand on the precipice of these advancements, it becomes increasingly clear that the study of faint comets is not merely an academic exercise. It is a vital component of our quest to understand the cosmos. Each comet we track, each moment of observation, serves as a stepping stone toward unraveling the mysteries of the universe. In the pursuit of these celestial wanderers, we are reminded of our place in the grand narrative of existence, a humble observer in a vast and ever-expanding universe, forever striving to illuminate the darkness with the light of knowledge. The implications of our efforts resonate far beyond the realm of comets, echoing through the corridors of time and space, shaping our understanding of the intricate dance of matter and energy that defines the cosmos. The act of tracking faint comets is not merely an exercise in detection. It is a profound step toward unraveling the origins of these celestial wanderers. Each comet, whether born in the distant reaches of its native star system, or flung across the galaxy by the gravitational tides of unseen forces, carries within it the imprint of its birthplace. The study of these objects compels us to ask a fundamental question: where do they come from, and what do they tell us about the universe beyond our solar system? Consider 3I Atlas, the third confirmed interstellar object to visit our cosmic neighborhood. Unlike the solar system's comets, which originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas hails from somewhere entirely external. Its hyperbolic trajectory, shaped by a velocity far exceeding the escape speed of the Sun, leaves no doubt about its extraterrestrial origin. Yet, tracing its path back through the stars is no simple task. The comet's arrival from the direction of the constellation Sagittarius, near the galactic center, hints at a birthplace steeped in mystery. Was it ejected from a young planetary system, cast adrift by the violent gravitational disruptions of a forming star? Or does it belong to a population of interstellar objects yet to be fully understood, wandering the Milky Way with no fixed allegiance to any single system? The implications of these questions stretch far beyond the comet itself. If 3I Atlas indeed originated from the thick disk of the Milky Way, a population of older stars with distinct chemical signatures, then its journey may span billions of years, predating the formation of our solar system. Such a discovery would challenge our assumptions about the longevity and distribution of cometary bodies, suggesting that interstellar comets may be far more common than previously believed. Furthermore, the detection of carbon dioxide, water ice, and other volatile compounds in 3I Atlas's coma offers a tantalizing glimpse into the chemical diversity of other planetary systems. By analyzing these materials, scientists can compare them to the compositions of solar system comets, seeking patterns that may reveal shared histories or stark differences in the conditions of their respective birthplaces. Even comets that originate from within the solar system, like C2025 F2 SWAN and C2025 R2 SWAN, offer valuable insights into the processes that govern the formation and evolution of celestial bodies. Their disintegrations, triggered by the sun's relentless heat and radiation, provide direct evidence of the fragile nature of cometary nuclei. These events serve as natural laboratories where the interaction between solar energy and volatile ices unfolds in real time, offering a rare opportunity to study the mechanics of sublimation and fragmentation. By observing these transformations, astronomers can refine models of cometary behavior, shedding light on the internal structures and compositions of these ancient relics. Ultimately, the journey of a comet from its birth in the cold depths of space to its fiery demise near the Sun is a microcosm of the broader cosmic story. Each object that enters the solar system is a messenger from the void, carrying with it the echoes of distant stars and the secrets of its own creation. To track these wanderers is to follow the threads of a vast and intricate tapestry, one that spans not only the solar system, but the entire galaxy. As we continue to refine our observational capabilities, we move closer to answering the most profound of cosmic questions. Are we truly alone in the universe? Or do these celestial travelers bear the imprints of countless other worlds waiting to be discovered? The pursuit of comets is more than a scientific endeavor. It is a voyage of imagination and discovery, a testament to humanity's unyielding desire to understand the universe. With each new detection, each fleeting glimpse of a comet's tail, we take another step toward unraveling the mysteries that lie beyond the horizon of our knowledge. And as we look to the future, one truth remains clear: the universe is vast, enigmatic, and brimming with stories yet to be told. In the vast, silent expanse of the universe, where time stretches into epochs and distances defy comprehension, comets emerge as fleeting spectacles, fragile yet resolute travelers from the fringes of the cosmos. They arrive like ancient letters, inked in stardust and ice, bearing secrets of distant origins and the raw materials of worlds. Among them, two comets stand out in 2025. C2025 F2, SWAN, a sun-grazing wanderer that disintegrated before fulfilling its fiery destiny, and 3I Atlas, an interstellar vagabond hurtling through our solar system at speeds unimaginable. Together, they are more than transient phenomena. They are cosmic envoys, offering glimpses into the architecture of the galaxy and the fragile dance of matter across eons. To gaze upon these comets is to peer into the abyss of time itself. C2025 F2, born of the icy depths of the Oort cloud, spiraled inward toward the Sun, only to unravel in a silent spectral demise. 3I Atlas, by contrast, defied gravitational bonds entirely, a relic from another star system, or a wanderer older than our own. Their stories are etched in light and shadow, in the physics of sublimation and the poetry of motion. They remind us that the universe is not static, but alive with motion, where every particle carries a history spanning millennia. This narrative unfolds as a meditation on these celestial visitors. It delves into their discovery, the science that tracks their trajectories, and the profound implications they hold for humanity's understanding of the cosmos. From the disintegration of C2025 F2 to the interstellar odyssey of 3I Atlas, we explore not just the mechanics of these objects, but the existential questions they provoke. What is the scale of our solitude in the galaxy? How do we reconcile the ephemeral beauty of comets with the vast, indifferent forces that govern them? The tale of C2025 F2, SWAN, begins with the Solar and Heliospheric Observatory, SOHO, a sentinel in Earth's orbit tasked with studying the Sun. Among its instruments is the Solar Wind Anisotropies, SWAN, camera, designed to map the solar wind using hydrogen atoms. Yet it was here, in the glow of Lyman A photons, that astronomers stumbled upon a ghostly visitor. On 22 March 2025, the SWAN camera captured a faint smudge against the backdrop of the Milky Way, a cometary nucleus, glowing faintly at magnitude 11, drifting toward the Sun. By 29 March, the comet had brightened to magnitude 10.6, its tail stretching 35 arc-minutes long. Observers marveled at its sudden evolution. Yet this vigor proved illusory. By mid-April, the comet's brightness waned, and its nucleus vanished, leaving behind a tenuous cloud of dust. The disintegration occurred before perihelion, the closest point to the Sun, when tidal forces and solar radiation would have torn it apart. The comet's orbit, calculated with painstaking precision, revealed a nearly parabolic path, an 80,000-year journey from the outer reaches of the solar system, where it had lurked for 40,000 years before succumbing to the Sun's gravity. The fate of C2025 F2 mirrors the fragility of existence itself. Its journey from the Oort cloud, a spherical reservoir of icy bodies at the solar system's edge, was one of inevitable decay. The sun's gravity tugged at it, accelerating its descent, while sublimation of its volatile ices created a coma and tail that shimmered briefly in the dark. Yet the comet could not withstand the sun's wrath. Its nucleus, likely composed of fragile aggregates of water ice, methane, and silicates, fragmented under the strain, dispersing into a faint haze. While C2025 F2 was a denizen of the solar system, 3I Atlas hailed from beyond. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas Telescope in Chile, this comet carried an unmistakable signature, a hyperbolic trajectory. Unlike the elliptical orbits of native comets, 3I Atlas's path was sharply curved, with an orbital eccentricity of 6.141, a number so extreme it implied the comet was not bound to the sun. Moving at a velocity of 58 kilometers per second, it raced through the inner solar system, its speed exceeding the escape velocity of the solar neighborhood. The origin of 3I Atlas is a mystery wrapped in the fabric of galactic history. Tracing its trajectory backward, astronomers pinpointed a direction near the galactic center, in the constellation Sagittarius. More intriguingly, its velocity component suggested it belonged to the Milky Way's thick disk, a population of ancient stars and interstellar material, some of which may be older than the solar system itself. If the comet's age aligns with the thick disk's typical stellar population, it could be 7 to 14 billion years old, predating the birth of the Sun by over 2 billion years. What makes 3I Atlas unique is not merely its interstellar provenance, but its chemical composition. Spectroscopic analyses revealed a rich mix of carbon dioxide, water ice and trace gases like cyanide and nickel substances, also found in solar system comets. This suggests that the processes that shaped comets in our system are not unique, but may be universal. Yet 3I Atlas's journey is a solitary one. Unlike native comets, which are influenced by the sun's gravity and planetary perturbations, 3I Atlas will escape the solar system entirely, carrying its secrets back into the interstellar void. 3I Atlas is a cosmic outlier, a relic from a time when the Milky Way was young. Its trajectory and velocity place it among the thick disk's inhabitants, a population of stars and objects that formed billions of years ago, when the galaxy was still coalescing from primordial gas clouds. The thick disk's chemical composition differs from the thin disk, where the solar system resides, with lower abundances of heavy elements. If 3I Atlas shares this heritage, its material may reflect the conditions of the early galaxy, offering a snapshot of the universe's formative years. This raises profound questions about the frequency of interstellar comets. Until 2017, no such object had ever been observed. The discovery of 1I Oumuamua and 2I Borisov, followed by 3I Atlas, hints at a hidden abundance of interstellar material. Perhaps these comets are not rare but simply difficult to detect, obscured by the glare of the galactic center, or lost in crowded star fields. If so, the Milky Way may be a cosmic highway, teeming with wandering objects that carry the fingerprints of distant stars. The age of 3I Atlas also challenges our understanding of cometary lifetimes. In the solar system, comets typically survive only a few thousand to tens of thousands of years before dissipating. Yet 3I Atlas has endured for billions of years, traversing the galaxy as a solitary traveler. Its resilience suggests that interstellar comets may serve as cosmic time capsules, preserving the chemistry of their birthplaces for eons. By contrast, the fate of C2025 F2 underscores the impermanence of cometary life. Its disintegration was not a failure, but a natural conclusion to its journey. Comets are inherently unstable, their surfaces pockmarked by sublimation and fracture. The sun's heat strips away volatile ices, while tidal forces stretch and tear the nucleus. For C2025 F2, the balance tipped irreversibly in mid-April, its nucleus dissolving into a haze of dust and gas. This process is a reminder of the delicate equilibrium that sustains comets. Their survival depends on distance from the sun, the composition of their nuclei, and the timing of their orbits. Amper's comet that ventures too close, like C2025 F2, becomes a victim of its own success. Its brightness peaks as it nears perihelion, but this proximity also ensures its destruction. Such comets are fleeting, their lives measured in centuries or millennia. yet their contributions to the solar system are enduring. The dust and gas they release enrich the interplanetary medium, seeding future generations of celestial bodies. Both comets, in their distinct ways, illuminate the interconnectedness of the cosmos. 3I Atlas, with its interstellar heritage, demonstrates that the processes shaping comets are not confined to the solar system, but are part of a broader galactic narrative. The presence of water ice, carbon dioxide, and complex organic molecules in 3I Atlas suggests that the building blocks of life may be widespread in the universe. If comets like this one were common in the early galaxy, they may have played a role in distributing these materials to nascent planetary systems. Meanwhile, C2025 F2 exemplifies the cyclical nature of cometary dynamics. The Oort cloud, from which it originated, is a graveyard of failed planetary embryos, a reservoir of frozen relics from the solar system's infancy. The gravitational influence of passing stars and the galactic tide occasionally perturbs these objects, sending them on long journeys toward the sun. Some, like C2025 F2, meet their end in fiery dissolution. Others survive to return, becoming periodic comets. Together, they form a bridge between the solar system's past and present, a testament to the ongoing dance of entropy and renewal. The stories of C2025 F2 and 3I Atlas highlight the limits of human foresight in the face of cosmic complexity. Despite our best efforts, we cannot fully predict the fates of these comets. C2025 F2's disintegration defied expectations, while 3I Atlas's precise trajectory remains uncertain due to the chaotic nature of interstellar space. These uncertainties are not failures but reminders of the universe's vastness and our place within it. Yet these gaps in knowledge are not obstacles. They are invitations to deeper inquiry. What unseen forces shaped 3I Atlas's path? Why does the Oort cloud release comets in bursts? And what triggers these eruptions? As we refine our instruments and expand our observational horizons, we may uncover new comets, each one a thread in the tapestry of the cosmos. The next segment will explore the tools and techniques astronomers use to track these elusive visitors. From ground-based telescopes to space observatories, the hunt for comets is a testament to human ingenuity and the enduring quest to understand the universe. But for now, we linger in the quiet aftermath of these celestial encounters, contemplating the silent messages they left behind. This script balances scientific detail with poetic reflection, adhering to the requested structure while emphasizing the cosmic wonder of comets. Each section transitions smoothly, inviting readers to contemplate the universe's grandeur and the fleeting beauty of its transient messengers. Comets are among the most enigmatic wanderers of the cosmos, their trajectories shaped by forces both ancient and ephemeral. While they follow predictable gravitational laws, their behavior often defies expectations. Sudden outbursts, dramatic disintegrations, and erratic fluctuations in brightness challenge even the most sophisticated models of celestial motion. For centuries, astronomers have sought to unravel the mysteries of these icy vagabonds, tracing their paths across the heavens with the hope of understanding their origins and fates. Yet, comets remain elusive, their unpredictable nature a testament to the vast complexities of the universe. From the disintegrating remnants of C2025 F2 SWAN, to the interstellar passage of 3I Atlas and the approaching spectacle of C2025 R2 SWAN, each comet presents a unique puzzle that demands both precision and humility in scientific inquiry. In this exploration, we examine how scientists attempt to model the erratic dance of comets, navigating the delicate balance between certainty and uncertainty in the pursuit of cosmic understanding. Modeling cometary motion requires a synthesis of classical mechanics and modern computational techniques. At its core, the movement of a comet is governed by Newtonian physics, with the gravitational influence of the sun and planets dictating its trajectory. However, the complexity arises when accounting for perturbations, subtle deviations, caused by the gravitational tugs of massive bodies, such as Jupiter or Saturn. These interactions can significantly alter a comet's path over time, making precise predictions a formidable task. For example, C2025 F2 SWAN, a comet that disintegrated before reaching perihelion, presented a particularly thorny problem for astronomers. Its orbital parameters, derived from limited observational data, left room for uncertainty in its aphelion distance. Some estimates suggested an orbital period of 1400 years, while others extended it to 20,000 years, depending on assumptions about its furthest point from the Sun. Such discrepancies underscore the challenges inherent in modeling comets that spend most of their existence in the distant, unobservable reaches of the solar system. In contrast, the interstellar Comet 3I Atlas offers a different set of challenges. With an orbital eccentricity of 6.141, it follows a hyperbolic trajectory, meaning it will not return to the inner solar system after its brief encounter with the Sun. Its extreme speed, over 58 kilometers per second, confirms its interstellar origin, but this very speed complicates efforts to predict its activity. Unlike native comets, which are subject to consistent heating patterns as they approach the Sun, 3I Atlas's trajectory places it in a dynamic state of flux. Its coma, a cloud of gas and dust surrounding its nucleus, evolves rapidly due to the sublimation of volatile ices. Observations from the James Webb Space Telescope and the Hubble Space Telescope have revealed an unusual chemical composition, including significant amounts of carbon dioxide and trace elements such as cyanide and nickel. These findings suggest that 3I Atlas may originate from a different star system, carrying the signature of an alien environment. Yet the exact mechanisms driving its activity remain shrouded in mystery, requiring continuous monitoring to refine predictive models. The case of C2025R2, SWAN, further illustrates the intricacies of cometary modeling. Discovered near perihelion, this comet's orbital parameters are partially known, but its future path remains uncertain. Its closest approach to Earth, occurring in late October 2025, raises the possibility of a meteor shower, though the likelihood depends on the survival of its debris trail. Unlike C2025F2, SWAN, which disintegrated prematurely, C2025R2, SWAN, appears to be holding together, at least for now. However, its potential for sudden changes in brightness and structure necessitates ongoing observation. The comet's rapid brightening from magnitude 11 to magnitude 8 in just a few weeks highlights the difficulty of forecasting its evolution. Scientists must rely on a combination of historical data, real-time observations, and statistical models to anticipate its behavior, acknowledging that even the most advanced simulations cannot fully account for the chaos inherent in cometary dynamics. To address these uncertainties, modern astronomy employs a suite of tools, ranging from numerical simulations to machine learning algorithms. Probabilistic models, which incorporate uncertainty into their calculations, offer a more nuanced understanding of cometary motion. These models treat a comet's trajectory not as a fixed path, but as a range of possibilities, weighted by available data. For instance, when predicting the future course of C2025F2 SWAN, scientists consider multiple scenarios based on different assumptions about its aphelion distance. Similarly, for 3I Atlas, which will eventually exit the solar system, models account for the comet's velocity and direction to estimate its long-term fate. By integrating these approaches, astronomers strive to balance accuracy with adaptability, recognizing that the universe itself is an ever-changing entity. Despite these advancements, the limitations of current models are evident. The low-resolution observations from instruments like the Solar Wind Anisotropes SWAN camera on the Solar and Heliospheric Observatory (SOHO) introduce uncertainties in initial measurements. For example, the discovery of C2025F2 SWAN was complicated by the fact that its coordinates were initially off by 2 degrees due to the camera's resolution. Such errors ripple through subsequent calculations, affecting predictions about its brightness and disintegration timeline. Similarly, the detection of 3I Atlas relied heavily on serendipitous observations from the Vera C. Rubin Observatory and NASA's Transiting Exoplanet Survey satellite TIRSA, underscoring the role of chance in cometary discovery. These challenges remind us that while science provides powerful tools for understanding the cosmos, it is ultimately constrained by the data we can collect. The integration of new technologies continues to refine our ability to model cometary behavior. High-resolution imaging from the James Webb Space Telescope and the Hubble Space Telescope has revolutionized our understanding of cometary composition, allowing scientists to analyze the chemical signatures of ices and gases in unprecedented detail. For 3I Atlas, These observations have revealed an abundance of carbon dioxide and trace amounts of water ice, suggesting a different evolutionary history than native comets. Meanwhile, ground-based observatories, equipped with adaptive optics and large aperture telescopes, provide critical data on cometary activity, capturing subtle changes in brightness and structure. These advancements not only enhance our predictive capabilities, but also deepen our appreciation for the diversity of comets that traverse the solar system. Yet, even with these tools, the fundamental unpredictability of comets persists. Their behavior is influenced by factors that remain poorly understood, such as the internal structure of their nuclei and the distribution of volatile materials beneath their surfaces. AMPER's sudden outburst, like the one observed in C2025 F2 SWAN, can dramatically alter a comet's trajectory and brightness, rendering prior predictions obsolete. Similarly, the disintegration of a comet's nucleus, as seen in C2025 F2 SWAN, introduces entirely new variables into its motion. These phenomena highlight the limitations of deterministic models, which assume a stable and uniform response to external stimuli. Instead, comets demand a more holistic approach, one that acknowledges the chaotic interplay of forces shaping their journeys. The pursuit of cometary modeling reveals a profound truth about the nature of scientific inquiry. Even as we strive for precision, we must accept the inherent unpredictability of the universe. Comets, with their capricious behavior, serve as reminders that our understanding is always partial, shaped by the tools we possess and the data we can collect. The disintegration of C2025 F2 SWAN underscores the fragility of celestial bodies, their survival dependent on delicate balances of pressure, temperature, and structural integrity. The interstellar journey of 3I Atlas challenges our assumptions about the origins of comets, forcing us to reconsider the boundaries of our solar system and the vastness of interstellar space. The approaching spectacle of C2025 R2 SWAN offers a glimpse into the dynamic processes that govern cometary evolution, yet its future remains uncertain. These discoveries compel us to confront the limits of human knowledge. While we can calculate orbital trajectories with remarkable accuracy, we cannot fully anticipate the consequences of a comet's internal activity. The sudden brightening of C2025 R2 SWAN from magnitude 11 to 8 in a matter of weeks demonstrates how quickly a comet can defy expectations. Similarly, the detection of cyanide and nickel in 3I Atlas's Comet suggests that comets may carry materials formed under conditions unlike anything found in our own solar system. These revelations challenge our understanding of planetary formation and raise questions about the prevalence of such materials in the galaxy. Moreover, the study of comets extends beyond their immediate trajectories and behaviors. They serve as cosmic messengers, bearing the imprint of their distant origins. The interstellar comet 3I Atlas, for instance, may have traveled billions of years before crossing our solar system, carrying with it the history of a star system we have never observed. Its high vertical velocity component places it in a unique category, distinguishing it from the thin disk population of stars in the Milky Way. This classification hints at a deeper connection between cometary dynamics and galactic structure, suggesting that comets may play a role in mapping the unseen architecture of the galaxy. The challenges of cometary modeling also reflect broader philosophical questions about the nature of prediction in science. Are we truly capable of anticipating the behavior of complex systems? Or do we merely construct narratives to make sense of the unknown? The disintegration of C2025 F2 SWAN serves as a poignant reminder that even the most meticulously crafted models can falter in the face of nature's unpredictability. Yet this uncertainty is not a failure, but a feature of the scientific process. It drives innovation, compelling us to refine our methods and seek new ways of understanding the cosmos. As we continue to observe and analyze comets, we must embrace the tension between knowledge and ignorance. The universe, in its infinite complexity, resists complete comprehension, offering instead glimpses of its grandeur and mystery. Comets, in their fleeting appearances and enigmatic transformations, embody this duality. They remind us that the pursuit of understanding is not about achieving final answers, but about cultivating a deeper appreciation for the vast, unfolding story of the cosmos. As these comets reach their peaks, whether in brightness, activity, or significance, they invite us to contemplate their roles in the broader tapestry of the universe. C2025 F2 SWAN, with its tragic disintegration, serves as a poignant reminder of the fragility of celestial bodies. 3i Atlas, an interstellar traveler, challenges our perceptions of the boundaries of our solar system and the interconnectedness of galaxies. C2025 R2, SWAN, poised to potentially create a meteor shower, offers a tangible connection between cometary debris and terrestrial phenomena. Together, these comets exemplify the dynamic, ever-changing nature of the cosmos, where order and chaos coexist in a delicate dance. Their stories transcend mere scientific data points. They resonate with the human experience of wonder and curiosity. Each comet, in its unique trajectory and transformation, becomes a symbol of the universe's capacity to surprise and inspire. As we continue to observe these celestial wanderers, we are reminded that the pursuit of knowledge is not a linear path, but a spiral journey, where each discovery leads to new questions. In the next segment, we will explore the deeper significance of these comets, not only for science, but for our collective understanding of our place in the cosmos. Through their transient brilliance, they illuminate the vast, mysterious expanse of the universe, urging us to look beyond the familiar and embrace the unknown.